sit where you don't have to be in the middle of things. It's your call.
I feel Ludwig has young legs. That's all I'm saying. Hey, everybody. Anyway, great to see everyone. Right, so where to begin? So this is joint work with a bunch of awesome people, and I think really pushing on a lot of really interesting empirical work. And I think I'm not going to say that the talk will be uncontroversial. So if I say anything that makes you angry, that's from me. And if you say anything that's like, wow, that's awesome, that's from one of these folks. Let's just keep it that way. All right, so I know this is a workshop on deep learning, but I'd like to start with machine learning. I just want to talk about machine learning. And I want to talk about kind of the conventional wisdom that we give to our undergraduates. Jonathan here teaches hundreds of them. And so I don't know how many of these things you tell them. Well, you can go through them. One, that like somehow to have a good predictor, you have to balance bias and variance, right? And that you really should not perfectly fit your training data. And that's a no-no. We definitely teach them that, right? And that you have to, he already knows. He knows the punchline. This is the sad part. And we know that high capacity models, right, when you have really big ones, shouldn't generalize. So you want to keep them small because if you that's stuff you show them the first day trying to do one-dimensional polynomial regression, right? And you don't want to optimize high precision. Non-convex optimization is hard. And I think everybody in this room at this point knows that none of these are true, right? It's weird, right? So we've all kind of come to the terms that none of these things are true, and yet we teach in our undergraduate classes. I'm trying. It's really hard to teach them anything else, to be honest. Nuance is really difficult at the undergraduate level, especially when there are 700 of them. So I think it's a kind of complicated thing. But it is this weird thing that we're in this weird regime where everybody here knows that none of these are true. And so I kind of want to push in a little bit on some other things that we tell people that also maybe aren't true kind of in this talk, just in case you don't believe me. Okay, first of all, what do I mean by machine learning? I mean something very narrow, right? For me, when I say machine learning, this I would upset some of my colleagues, notably Mike Jordan, but I upset some of my colleagues when I say this is all machine learning is, right? It's just making predictions from examples. I have a set of something, I have a set of something else, and I want to find prediction functions that map X to Y. I know there's more than that, but this is the backbone. This is why all of you are here. This is why there are $1 billion invested in this. And so the whole idea is that how do we actually estimate these things? We estimate them from data. We collect as many training data points as we can. We estimate them from data, and then we just hope that this works on other data. Right? And that's the big hope. That's the big hope, is that we have a lot of data. If we collect enough of it and we get all edge cases, we can drive our cars, whatever those edge cases are, right? And so that's the notion of what machine learning people mean by generalization. So I actually think generalization is machine learning is full of words that confuse the listener. They're just designed to confuse you. So generalization, when I say that to you, that means that you learn how to throw a baseball and then you can throw a softball. That is not what we mean in machine learning at all. In machine learning, we mean if you know how to throw a baseball, you know how to throw a baseball. And as long as it's a regulation baseball made to regulation weight, you're going to be able to throw that baseball. And that's not at all what normal people think, right? So the idea is that you give me n examples from a distribution. I would like to find a good prediction function on these examples. I have some loss function that I believe is a reasonable thing that I would like to minimize in expected value, meaning that if I have some new thing that comes from this distribution, I'd like to be able to do well. That's not known. So what you do instead is you replace it with the sample average, the empirical risk, and you minimize this. And like the only thing we're allowed to do, where's wrong? It's over there now, right? The only thing we're allowed to do now is minimize this using one of two algorithms. Right? There are like 3 things we can do. We minimize it that way. And then, of course, our generalization error is just the difference between these 2 things. Right? And so the question is, if we can compute this one, when is that a good or bad proxy for the other one, right? That's what we mean by generalization. It's just a badly named term, but it's a very interesting problem. And it's kind of like the core problem in machine learning, right? And the core theorem of machine learning is that the population error that we really care about is just equal to the training error plus the generalization error, right? And that's like the foundation of 10,000 papers, right? We've all done that at one point in our lives, right? And so we can measure this one, and then we do a lot of thinking about why this should be small.
That's a definition, not a theorem.
I mean, this requires like the associative property. There's stuff to be done here, right? I think we can quibble a little about derived versus axiomatic, right? So I think, right. And so what can we take away from this? We know that if you have a small training error, that means that the risk itself is just, you're really only leveraging generalization error, right? So if your training error, for example, is 0, you're just hopefully know somehow that the generalization error is small. And 0 training error, we know, does not imply overfitting, even though that's another thing that we do tend to sometimes gets lost in the weeds. Like, for example, the paper I really like, which won Test of Time at NIPS last year by Bousquet and Boutou, right? Has this thing saying that you shouldn't run SGD too long because at some point, all of these terms should be 1 over square root of n. But we know that's not really true, right? I mean, just because this is 1 over square root of n doesn't mean this one's 1 over square root of n. And just because this is 0 doesn't mean this one's small. So, you know, it's useful. It's a useful way of thinking about it. But sometimes we overfit to what kind of these papers say, right? So don't want to say it's not always true, but it's a useful way of thinking about it. Another way that this one ends up sometimes presented, this is how I learned it. Not everybody presents it this way, is that you decompose. It's the same proof, though. Is you decompose the error into 3 parts, right? So you compare your error of your estimator versus the error, the best thing in the class of stuff you've been looking at, right? And then you compare the error of the best in the class to like what the true prediction function, the best population risk monitor is, and then you kind of are stuck with some bias at the end, which is this is just the irreducible error that you can never get away from. And to whichever one you like more, I don't care. I like this one just because it allows me to attack. This is my least favorite figure. I'm kind of going to be at the core of the talk today, right? So this is my least favorite figure. It's from Hastie and Tibshirani. I like those guys, but again, this figure, we read way too much into this, right? So somehow the idea here is that we have to balance bias and variance in order to get good model complexity. Again, you can do that. You can do that, but this is by no means the only way to generalize. And we know this. Okay, I learned this because of deep learning. And to be fair, I learned this before and had forgotten it. And I'm going to talk to you about that in a second. But I learned it again recently because of deep learning. That you can just make these models gigantic and they generalize. And so in a very unpopular paper that I know lots of people who have my back to right now don't like, we read a bunch of, not you. Sorry, maybe just one. Anyway, so we read a bunch of experiments on the CIFAR-10 data set, everybody's favorite data set, where we have chickens, I can't remember what that is, frogs, deer, and trucks. And so this is a 10-class classification problem. It's relatively high dimensional, has 3,000 dimensions because of the pixels, 50,000 data points. And if you take, what we found is that you could either get a loss to be non-zero. Here, this is the loss. This is the log loss, which is not the classification accuracy. You could work really hard to get this to get your generalization error down, or in this case, the test error. Or you could just run it to 0, essentially just taking this configuration and turning off all the regularization, run it to 0. And while you see a drop in accuracy, you don't see a gigantic drop. So the test error increases, but only by about 5%. And moreover, if you just pick a bigger model, now you're considerably better than the original AlexNet. And if you pick an even bigger model, you keep going down. I don't know if Chi-Wan's here. I'm sure he tried something even larger. We just ran out of time. So, so somehow here, the regularization parameters turned out to be just knobs that you could tune. So you could also tune architectures. You could tune lots of things and keep pushing this error down. And indeed, we kind of saw the same thing on Imagenet, where here we have chicken, frog, deer, and truck, much more clear, right? I think at some point. Anyway, and so we looked at an Inception model inside Google. I really don't like this experiment. I just want to show it just to kind of give evidence that this happens on larger data sets. The reason I don't like this experiment is that because of the way that these things were trained inside Google at the time, we were able to run about 6 runs. I think had we used, I think one of the more valuable things that's happened to the community is this Dawn benchmark. Had we just used the Dawn benchmark, we would have been able to run hundreds of experiments and got much better here. But all we were able to do here was toggle flags inside some Google 3 models. And so in particular, in this case, what we could do is we could turn off the LT regularization, and we could turn off the data augmentation, and you could still get perfect interpolation. And even note that the top 5 accuracy here is only 19.3. Top 5 error is only 19.3. you try to get to something that has 19.3% error from 0. It's really hard. So it's significantly worse than what the Inception model is getting. But again, it's not catastrophically bad. This would have won. This would have beat AlexNet the first time around. Right? So it's good accuracy. Yeah.
So you're saying that you're complicating the idea that there should be some balance between bias and variance.
Yeah.
I'm wondering how seriously you mean that, because like we heard several talks talking about implicit regularization, which is going to be a form of control of variance. So what?
Yeah, so I don't really, so okay, there is talk of implicit regularization. I guess what I would say is that we started to just look at more models. What we started to do is stop looking at just this individual models, or 4, and we just started to download more. This actually became a big trend in the research group. This is something that Becca Rolla started, kind of pushed us on this direction, and Ludwig Schmidt, who's sitting here, kind of really pushed us even further in this, kind of like using GitHub as an experimental resource. So you just git pull some models and then see what happens on a bunch of things. So this is a scatter plot. I don't really buy that parameters in a neural network is actually that meaningful, but you can see that essentially as you make the number of parameters bigger, the models continue to get bigger.
What's the blue line and what's the red?
The blue line is just the minimum error, and the red is just a scatter plot of some models.
Minimum error what?
At a particular model size.
Oh, it's like it's supposed to be a curve of those red.
I'm just taking the minimum error of the reds, yeah. I mean, like, I'm not saying that they're all true. I'm just saying you could keep making them bigger.
So this is not very
Huh? What's that?
The blue line is supposed to be to the right and the red dots?
It is.
It's not. Okay, but fine. It's just the
What are you not seeing? The third one happens on the x-axis. The last one happens on the x-axis.
It's because it's using like the step pre-step code. It's like a Python issue.
Anyway, that's fair. Do you want to do a pull request while we're here? We can go find. Actually, if I can call Fernando, we can get him on it. Anyway, so here.
I'm trying to understand if it was actually something else because it's just
here. There's no plot on this one. There's no plot on this one. This is just what's nice about this one. This is even better. What you do here is just remove models. And so now you see the trend. This is from so there's no you will not see there's no AlexNet or VGG on here. They kind of ruined it, but they're just up here somewhere. It's fine. Like the curve, you really care about this lower envelope. But this is the same thing kind of happens on Imagenet. You just keep making them bigger. What you'll notice is like we have log axis on the x, and linear on the y. So semi-log. This I pulled from a paper by some Google folks, because only Google folks would think it would be fun to train something with 600 billion parameters. Million. 600 million. Okay, that's reasonable. 600 billion was stupid, but 600 million is perfectly reasonable. Anyway, so that's that one. Keeps getting bigger. Here's from Misha. This is from Misha's talk yesterday. Well, actually, I made it, but it's fine. It's the same plot, right? We see the double descent. So this is now random feature models, where we just keep adding random features and see how the accuracy goes. And even though it does go up, it kind of comes back down as you make the models bigger and bigger.
Although you're controlling variance with the norm, no?
I don't know. Am I? Well, I'm just interpolating. So this one is just interpolating. I'm not doing anything.
How are you interpolating?
Huh?
You're doing minimum solutions.
Because it's a kernel.
How are you finding the minimum? There are multiple interpolating solutions. How are you finding yours?
So in this case, it's minimum Euclidean norm. Right. Yeah. Although what's interesting is that I like this plot better, is that if you don't do minimum Euclidean norm, but you just go use ridge regression, so you allow yourself a tunable parameter, now that dip goes away. Now it just gets better. So, so I don't know, right? So this is not minimum norm. This is ridge regression, and then that bump goes away. Huh?
You choose a ridge actually.
Yeah, you've picked the best ridge.
For each.
For each dot, I picked the best ridge. It's not a constant one. I picked the best one for each, and you're going to see why in a second. This is the best one for each. It's the lower end. So we're going to see why in a second.
Of which number of parameters?
Huh?
You choose the best ridge for each number of parameters, so you just it goes down, right? With the number.
It's going down with the number of features given. Like for the best value goes down.
For every value, every number.
Every number is so yes. So sorry. In this case, I'm not taking the best one from here. I'm not taking the best of these two. It is just if I tune this, what's the best I can do just on this one fiber? Yeah. Anyway, here is a paper, something I stole from Peter. This is from a NeurIPS. Actually, it was NIPS at the time, but NeurIPS tutorial from 20 years ago. Here he was doing boosting. Remember boosting? Some of us do, right? Barely. And what do you see here? Well, I have, first of all, note the semi-log axis. There we go, semi-log x on the, that's pretty neat. And you add parameters and boosting, right? You increase your model size with every step. And so now I have the models get bigger and bigger and bigger, and the test error keeps going down. I think so that was interesting, right? So that was small data machine learning, but it still seemed to have a thing. This is another really interesting one, which I pulled from a CACM article by Bell and Corin describing how they won the Netflix prize. And they saw, again, the same thing. They have different kinds of models, but they kept making their models larger, right? Again, we have semi-log x on the number of parameters, linear in error, and you see this thing kind of continue to keep going down the bigger and bigger you make your model. So I think there is something interesting there. So you're seeing two things. One, making the model really huge doesn't it has a ton of capacity. Maybe you're controlling it with various kinds of regularization of some form or another, but it always just seems to make it bigger and worry about that later. Does seem to be a good take home. And the other thing is that you see significant diminishing returns, right? I mean, if you have a log x-axis, I mean, this does mean that eventually you have to give up. Even Google. Eventually you have to give up. So I'm not sure that this is necessarily going to get us to like that irreducible error we'd like to get to.
And this is not millions of parameters, right? Like,
There's a x-axis is
No. It's not a typo. Not a typo. 100,000 million. That's like Carl Sagan. It's 100,000 million parameters. That's a deep cut. What? Huh?
It's bigger than Imagenet, but the numbers don't match because it's 1,000 in the middle and
that would
1,000
be
on the
bigger
right.
than the Imagenet.
100,000 million.
Yeah, probably. That's 10 billion.
Yeah.
100 billion.
Yeah, because the Netflix price is
It's
like
100 billion.
users 10 grand.
Anyway, I didn't make this plot. You can go ask them. I read it both. They don't get there, right? It's log.
Yeah, but even what are the numbers on the
10,000, huh?
What are the numbers on the curves?
I don't know.
They don't actually line up. Right?
Yeah, 50 is above
No,
1,000.
1,500
No,
is
these
like
mean
the
different
high
things. These mean different things. You have to read the caption that's not here. Sorry, maybe I should have edited it. These things do not mean, they're in the caption, whatever those mean. Huh? I don't know what those numbers are. These, huh?
Number of factors,
Yeah, number of factors.
The number of factors. Are you sure?
basically.
Did you read the paper?
No, I
It's been a while.
I went for the figure caption.
Pause at this step. Anyway, somebody can look it up. It's in CACM. It's cool. They did a lot of good work. Well, let's go back to this one. So look, here's what I would like to say. Like, there are crazy diminishing returns. One. Two, it does seem making the model bigger for a fixed holdout set that we fix in time for the history of the universe does make that test error go down. But that's also not generalization error. Right? If you do a holdout split, where you take a train set and you take a holdout set, and then you just fix that holdout set forever, maybe what's happening here is you have these giant models have enough fluctuations in them that you can actually leak a lot to the test set and overfit to this one holdout set that you fixed forever. So this leads to a question. Where I'll spend most of the rest of the time of the talk. Where's the time? There it is. Perfect. No, we have plenty of time. Good. So yeah, that's the rest of the talk. So maybe what's happening here is you make these models really big, and that allows you to overfit on this one holdout set. And so there's only one way to check, right? Which is make a new holdout set. I think. Is there a better way? I don't know, but that's what we did. We made a new holdout set. And let me explain how. So here is progress on CIFAR10 over time. So if you just use raw pixels and do linear classification, you get 37%. Accuracy. I just realized we've switched from error to accuracy. Hopefully it will be clear from context. I'll just say accuracy. Now we have 97.1% in 2017. In 2019, what is it? Ludwig knows these numbers. What's 99 point what?
0, I think.
99.0. Oh, sad. So we got, there's still time to write more iClear papers, everybody. We got 10 more ticks. So this is like our deep revolution here, right? This is the deep revolution, happened in 2012, and we just keep making progress, make them bigger, get them more capacity, make these models really large. These shake models are huge. Wide resonance also are just enormous, right? And try to get them to fit. And the question is this overfitting, right? Right? Because this early part, we can match with shallow methods. I mean, actually, you can get to like 80. I can't remember the number, but there's some work by Shyam Kakade, Alec Agarwal, Greg Valiant, and Lei Song, like from 2013. So that if you just do random features, you can get to about 85% accuracy using just dumb random features. So shallow stuff can get I mean, it was big. So it was also a large shallow model can get to about 85. And so the question is, all we're doing here is just overfitting to the test set by graduate student descent? That's the question. So we're going to check, and we're going to check by building a new test set. Now, what does that mean? So it turns out that the CIFAR10 creation process is super well documented. And it was documented by the folks at Toronto who made it in the first place. And so there is a lot of details about how they did it, and in particular, where they got their images to begin with. And that comes from one of my favorite data sets ever. It's called the 80 million tiny images, the tiny images data set. And it was curated by Antonio Torralba, Rob Fergus, and Bill Freeman. And they made beautiful like scatter plots of like all the images on the internet and these like mosaics, and just seeing like how everything varies. It was a very cool kind of looking at what kind of the things are out there that you can just get off the internet in 2008. So it'll look different now, but in 2008. So the reason why they were thumbnails is because they wanted to make something that you could store and then do all sorts of visualization and studies with. And so from these thumbnails, they subsampled 60,000 using a process that was very well detailed with human, not experts, but human labelers. And they tried to get down to these 10 classes. And so can we get an IID resampling? Well, there's out of 80 million images, we only took 60,000 out. So the hope is maybe we could sample some more. Maybe not even that many more. How many do we need to actually get something that we believe? So I think Ludwig did his error bar calculation and said 2,000. That's what we said. That was what he wanted, 2,000 new ones. And so in work that I did not want to get involved with, Ludwig, Becca, and Weishall labeled, actually mostly just Becca and Ludwig, right? This one? For this one, it was Ludwig and Becca labeled tens of thousands of images in the tiny images data set. And we got a new test set of size 2,000. And again, there are fine details about like what counts as a boat, what counts as a car, and this kind of thing. And we tried to match as closely as possible. So what did we see? Okay, so the first thing we see is we take VGG16, everyone's favorite network, right? I guess. Anyway, this is the big one. And what we saw is a huge drop in accuracy, right? There's an 8% drop in accuracy from the first test set to the second test set, which is much bigger than you would expect by 1 over root n in some reasonable capacity. That's big. I mean, this is if we put a little confidence interval about where we should be. This dashed line is the reproducibility. You'd hope that the confidence interval would hit the dashed line. That would mean, okay, there's, these, we'd say, hey, haven't been overfitting at all. I thought, oh, that's great. That's great. So it's clear what's going to happen because, right, 85.3 was right in the ballpark of what people had seen you could do with just shallow learning. Right? And so clearly what's going to happen, let me just, I don't know if anybody's read this paper yet, but clearly what I thought would happen and what I put my money on was that, now the shallow learning stuff will just be here and we'll just see that we'll just get a saturation. So we've just been adapting and we'll just see a saturation up here and everybody will be equal. And, right, and that was why this big drop. And so here's our random features. And that's not what we saw at all. Not what we saw at all. I lost money. Actually, I didn't lose money because everybody else bet the same. So it's good. There was no house in this case. Right, bigger drop, 12% drop. So that went from 85.6 to 73.1. Bigger drop. Really depressing. And the shake model only had a 4% drop. This one that had super high accuracy. So we saw exactly the opposite of what our hypothesis said. Right? Our hypothesis suggested that maybe the big models were able to just fluctuate themselves to overfit to this one particular holdout set. And if we draw a new holdout set, we'll see some sign that they had adapted to it. But we saw the opposite. In fact, the ones that have the better test error on the original test set have a better accuracy on the new test set.
Oh, did you have the original weights for these models, or did you have to retrain them?
We did. Well, we did retraining in the paper, but in this case, this was just original weights.
Okay.
Yeah, in this case, it was original weights. We did some retraining, but again, this is why GitHub as an experimental resource is so powerful. People post the weights in the repos. Saves you tons of time. So it actually is a kind of really, it's very, you don't even need a GPU, right? you can just download stuff that people have already done, change a parameter here, do some kind of experiments. As long as you don't have to retrain too much, it's pretty interesting.
Is there a way to measure, I mean, we're going to get this later, is there a way to measure the discrepancy between the original distribution and the distribution you created? Like, I mean, measure how
a great question.
How Becker and Ludwig's labeling was different from the original labeling.
So Nati already picked out like kind of the big problem here, right? So there was clearly, this is not an IID resampling. Right? It's not an IID resampling because Becker and Ludwig are not, we don't know who the Toronto folks were. Probably some paid undergraduates, and they're not Becker and Ludwig, who have never been to Toronto, right? That's very good. So there is a, yeah. So it's not perfectly IID, right?
No, sure, but is there a way to measure that?
Discriminate.
This is a great question, but let's come back to it. Let's come back to that. On the empiricals?
It's train a classifier.
Yeah, but no, you can't tell the difference if you train a classifier. Yeah, we tried that. Yeah. That's
Try just like a two-sample test on
I only have sample
features.
two sample tests on what? On features?
Yeah, even just on like
Why features? Oh, just individual features to see if you see significant things?
yeah, you can do that, or on representations and neural networks. But
We did not do any of this yet, but let me keep going
Wait,
because
so the images themselves I thought were from the same distribution. The only difference is in labels, right?
then they're not from the same distribution, right?
No, yeah, but the x's. The question is the marginal over x is from the same distribution.
Yeah, we would hope so, right? I mean, that you could probably check because there were some subselected to begin with, right? So if too many were subselected, then they're not going to be IID, and that's something I think we could probably.
Yeah, but that part did involve humans, so that part
Did not involve humans.
presumably be the same.
That's right. That's right.
Just the y condition on x might be different.
That's right. So what Nati's asking is just that probably the only thing that changed, probably, again, being generous to us, the only thing that's changing here is the labeling function, not of the human, the thing that's producing the y, not the thing that's producing the x. Probably. No?
No, I mean, in these labeling procedures, you never actually, as a human, decide on the y. You only decide whether you keep an image or not.
Oh, that's interesting. You only decide if you keep an image or not. So actually, that actually means that could be different. Go ahead.
Did you try taking the 50K training samples and the 10K test samples, just reshuffling everything, pulling out different 50K and seeing how it does on the 10? How
Yeah.
did that compare?
Do you remember?
Yes, no change.
No change. There we go.
No change compared to
change.
what?
What was
Ludwig,
you
it's
get
got-
the same numbers as you get on the existing tests. So if you fold the test set as a
Ludwig,
split into the training set, and then
So could it be that?
He just wanted to know if you could you interleave the two test sets, if you could, or sorry, if you can interleave some of the stuff into the training data.
In that case, it's going to show results that are similar to what people publish.
yeah.
So
But
could
you
it
have
be
to
that
train
the
everything.
entire, and actually, the fact that better models have a smaller drop suggests that maybe this all boils down to the test set that you construct being different, just like nothing?
It could be. It could be. I mean, well, so sorry. What are you suggesting?
So I was asking about.
So can we just wait? Hold on a second. So this is actually really important. This is really important. The fact that you've already moved on from the fact that there's no adaptive overfitting is shocking. Look, there's no adaptive overfitting. This is rule 1. Don't look at the holdout set more than once. That's rule 1. We look at the holdout set 50,000 trillion times at Google every day, 50,000 trillion times, and yet it doesn't matter. The better you do on this holdout set, this one stupid fixed holdout set, like it doesn't matter. That, I think really, before we talk about why the drop happens, just the fact that we don't see adaptive overfitting, it blew my mind. I did not think that would happen. I did not think that would happen.
Trying to ascertain whether you do not see adaptive overfitting at all, or whether you see the same amount of adaptive overfitting in different models. Right? So those are two different things, which so far from your results is not clear.
Wait, what does that mean?
So it might be, you have a gap, right?
Yeah.
Why is that gap? That gap could be because of two reasons.
Yeah.
One reason for the gap would be because there is
I
a
kind of agree. I kind of agree with Zico.
There is. I'm
Yeah, that's right.
I'm not putting it right,
Yeah.
but one hypothesis is the gap is due to adaptive overfitting.
Right.
But you see that in all the models,
Yeah.
roughly to the same amount.
Yeah.
Okay? The second hypothesis is there's no adaptive overfitting at all, and this gap is only because of the difference in the distribution.
Yeah.
Right? And we're trying to kind of, I think, this discussion
So
is trying
the thing is, to be fair, gonna be hard to. It's gonna be well. I think so. But
so, right?
listen, one second. I think it's gonna be hard to tell from CIFAR 10. And I think what's interesting is if we go to this other data set, that's more interesting anyway. I mean, maybe we can, Ludwig, but I think it's much more complete.
results and the Kaggle results?
Yeah.
Okay.
Yeah. I'm getting there. Maybe. I might be getting there. We'll see how long people want to stay through lunch. Yeah. Tangy was had his hand up for a second here. Go ahead. What?
Can I have a quick proposal? So if a backend Ludwig can have like 50K examples from this new data set, then you can train on this new data set and then test on the old CFAR tested. And
I don't know if we could get. I don't think we can get 50K. Yeah.
So the 80 million images are divided into keywords.
Yeah.
In tiny images. For each keyword, it's about 2,000 images, and some of the keywords are basically exhausted. So if you wanted to get another 50,000 images, it would actually be different keywords, and then it's a different stream.
Yeah, I think we could probably do more than 2,000, but I'm not sure where the limit is. Yeah.
Did you try labeling the ones that Toronto already labeled and checking for agreement?
Yeah. Yeah, that's actually in the paper. You can see at the end. Yeah. But also, the thing is, I only have two Becca. I have Becca and Ludwig. You know, they have limited cycles. You know, it's a problem. It's a problem. It's a problem. And certainly, I lost both of them. So it's really sad. Actually, that's really sad. Yeah, both of them. Well, no, Ludwig's staying. Sorry. Yeah. You didn't take him, did you? Good. Okay. Phew. That was news. Okay. No, fortunately, we have Ludwig, but we did lose Becca. She's graduated this year. Okay. Also, who cares about CIFAR 10? CIFAR 10 is this fun little thing that we all kind of like. We can train it, and it's interesting because it's like the first non-trivial thing we can get to. But you know, what captured people's imagination was this Imagenet data set. And the question is, can we do that one? Now that's harder because that's bigger. There's more labels. There's more, and even here, like these 1.2 million training images were not labeled in a lab. They were labeled using Mechanical Turk. So that's an opportunity, right? So now we can try to reproduce this data set and this procedure using Mechanical Turk, which makes it much more scalable. And we can make much larger, we can do much larger experiments. So how do we get this IID resampling of Imagenet?
Make one more point. Sorry to interrupt.
I'm getting my water. Go ahead.
I think maybe it's not as surprising as you say, given the fact that we can drive regular models to zero loss, something which we thought was impossible. And that's okay. This is like the community driving it's like community doing overfitting on the test set, and it's kind of the same effect at the meta level.
No, I don't think so. Again, like why don't we see a plateau? Anyway,
Maybe you don't see a plateau because it's not really overfitting on the
Why
test.
not?
That's right. That's why. Anyway, let me keep going. This is more interesting, Misha. The CIFAR 10 thing is so boring. Let me show you this one. This is much more interesting. Much more interesting. I promise. Much more interesting. Actually, if you want, we can go into some more nitty-gritty with this one. I have far more than I'm going to be able to get through, which is fine. It's fun. No equations. I have no proofs. I just have more plots like this. So this is kind of the interface that you would see if you were a Mechanical Turker getting paid to label images on the internet, which is basically how all of everything is made to work now inside all of the big 10 companies. They hire people and have them watch horrible, disturbing content and flag it for their algorithms. It's great. Wonderful world we live in. So in any event, so here's our images, right? These are supposed to be bow. Everybody can read at the top. A bow is, actually it's not quite clear, a weapon for shooting arrows composed of a curved piece of resilient wood with a taut cord to propel the arrow. And the task is click on every single image that has a bow. That's what the Turker is asked to do. Click on every single image that has a bow. So for example, these three have bows. These ones don't. And actually, these were three that were adversarially placed in here to make sure that the Turkers weren't cheating by us. Right? So what we did was we actually flagged all of these new. So in reproducing Imagenet, we tried to reproduce the query that was used to collect images, reproduce the things that were allowed, like including the date range from Flickr, reproduce the way that these things were labeled, and we also threw the old test set in here to see how those were labeled by these Turkers, which is much nicer than what we were able to do with CIFAR 10. And what's interesting here is that there's super high variability in it's like not everybody says the same thing. Obviously, there's going to be disagreement, right? Anybody who's working crowdsourcing knows this, right? You have the people who do these tasks, either they work too quickly or there's just nuance, right? So for example, this bow was selected 100% of the time by every Turker. This one was 70% of the time. Our heroine from Brave. I mean, there's a bow there. It's a little bit hard to see on this blown out screen, right? So there's lots of reasons. It's not center frame, so there's a lot of reason to miss it. This one now becomes a metaphysical conversation about what is a bow. My good friend Conrad Kerding says yes. So, I mean, neuroscientist. So, you know, I don't know. Everybody has their own opinion about what that is. And this one's wrong. And then 20% of the people decided this was a bow. It's a bow. It's not the bow we want. It's not the bow we want, right? Okay? So I think that's our issue, right? So this is not the bow we want. And so we actually had like the histograms for every class. For every class, 1,000 classes, we had histograms of the selection frequencies. And so when we actually sampled our new test set, we tried to match the statistics of the label from the original set with the new set. Also, Ludwig, Becker, and Weishall looked at every single image and made sure it was correct in the new test set, which is clearly creating a distribution shift. Yes? No. Yeah, we measured for that.
That was presumably done also for the old one based on that.
That's what Alex told me. Alex Berg told me, but anyway, it's not true. Yeah, you could go look. Go look. That's actually the other amazing thing about all these data sets. How many people have ever looked at the images in Imagenet? I mean, you don't need to. You just watch the curve go down. But like, you know, like actually inspecting them it's like we kind of have decoupled ourselves from actually any of the domain expertise. It's not a common.
It's actually quite entertaining when you do.
Yes, it's quite entertaining when you do. I agree with Alexander there, right? Okay, so punchline, right? We see exactly the same thing. We see exactly the same thing we saw in CIFAR 10. A bigger drop, technically speaking, is a 10%. It's like a 10% drop at the top here for the best ones. But we still see a positive slope. So the models that have models that fared better on the original set fare better on the new set, but a little bit. It's not as pronounced as it was for CIFAR 10, but we definitely see a positive slope in our fit. But we do still see this significant drop.
So how is the new labeling of the old test set or training set or whatever the old image? I mean, you said you also labeled the old image.
We labeled the old ImageNet just to match the selection frequencies from our. So okay, was there a distribution shift already? You already pointed out that Ludwig and Becker are not the same as.
Right, but now you can actually measure this because you said you took actually images from the old ImageNet.
And then we matched their sampling frequencies.
But you also in the process you also get labels for that.
Yeah.
So you can actually tell us what is the agreement between the new labels and old labels.
I'm saying we sampled. We have a bigger pool. We didn't actually. Our new test set was a bigger pool of images, and we sampled from that pool to match the statistics of the old test set.
Oh, just the statistics. You didn't actually include. I thought you said you included the old actual images.
In this, no.
No, we did include. So
no, but Nathan's saying in this evaluation set. There are no old images in here.
In your relabeling.
Yeah.
When you relabel.
Yeah.
You took an old image.
Yes.
And there isn't a sign label to it.
Yeah.
And you got a new label for it.
Yeah.
Okay. You can measure how well the old labels, if my labeling takes those images, on those images, take the predictor defined by the old labels.
Yeah.
Okay, that has 100% accuracy, on old accuracy.
On the old validation images, it doesn't, right? It has 7.
This is you're only looking at old images.
Yeah.
You're looking at old images. And
Validation images. Old validation images. Yeah.
Defining the predictor
Yeah.
as the old label of it. That
Yeah.
has 100% accuracy.
No,
By
why?
definition.
Why?
No, it's just the labeling, right?
Because you're taking the labeling and you're comparing them to the labeling.
But
That's
it's noisy,
100%
man.
accuracy.
It's noisy. No, man, it's noisy. It's still noisy. Again, so the orange line here,
Fine,
not
no,
the
fine,
or.
okay, fine. Then take the it's
Sorry.
then but even if it doesn't matter. It's nice. You're taking the label that was as it appears in the training set. Every image only has a single label.
Yeah.
Okay, it was generated using some procedure.
Yeah.
Take that label as the labeling.
Yeah.
And measure how well those predictions predict the labels that was assigned by your process.
You could do this.
So I think that's only Ludwig can do.
That's not. Also, Ludwig's right. That's not how these data sets are built at all.
I'm able to imagine this entire process.
Yeah, I think this is actually also really important. Hey, Ludwig, let me.
Pipeline
I got that.
overlay.
I've got the. It's okay. It's okay. I got the for it. But I know. I'm also used to this. So it's a procedure. It's a procedure. It's also true, right? That none of there's no these data sets are not made by labeling images. Again, like what happened, right? You show people you query, and then you test correctness as to whether or not they go in or out.
Okay.
It's a weird process. The other thing that's really interesting, by the way, that we take for granted, the question you ask the Turkers is, which of these images contains at least one type of object, bow? That is not the classification problem that everybody is now weightlifting against each other for. The question we have now is just label the damn image, and it has one label, and that label somehow comes out. And we know that, like, why is this a bow? I mean, this contains a bow, but this is the I forgot her name. What's her name? She's from Brave.
Merida.
Meredith, okay, it's not Elsa, that's Frozen, I know that one. So yeah, right? So again, like if I asked you, what is that image? You could describe so much. Is Elsa in a forest with her bow on the branch here? Anyway, there's like Meredith, excuse me. Anyway, right? So it's like a much more complicated thing. And what we evaluate is very different. Let me
Why
just...
didn't you ask that from the mechanical Turkers?
Huh?
You could have asked the same question you asked from mechanical Turkers.
I mean, dude, I didn't make the original Imagenet data set, so
You could have asked what's in the image, and the mechanical Turker is
But originally it was asked, the question was asked in the original dataset as well.
we asked exactly the same question that the Imagenet people asked. I'm just saying, it's the exact same question.
So maybe you should redo Imagenet.
Oh my God. Maybe you should redo Imagenet. I'm not doing that. By the way, this costs tens of thousands of dollars. It's really expensive. It's really expensive. And so anytime you want to say you want more, right? I mean, just note that this is a very expensive project. And thank you to Microsoft for generously funding part of the late line. Anyway, could I just... let me just blaze through does anyone mind? I have two more examples. Do you want? I mean, everyone wants to go to lunch. Yeah. Okay. Here, two things. I do think, and you could fight with me and maybe try to find more evidence that we do not see adaptive overfitting, or at least it's not obvious, but we do see significant fragility from distribution shift, and the distribution shift is just humans disagreeing with each other, barely. I mean, it's not even humans disagreeing with each other. It's just that there were mechanical Turkers in 2011, and now there are mechanical Turkers in 2019, and that's different people. Most likely, I don't think people Turk for that long. There might be some OGs, but yeah, go ahead.
Just a quick question about the plot. So this is all parameters from the models trained on the old data set tested directly against your new labeled data set.
No retraining, no nothing. It's just take the thing, take the weights, don't have to retrain, because otherwise that would be really expensive again, unless they were trained with the Dawn bench. Some of them are really slow. Some of them come from Google, so they're really, really slow. And so you have like these things that are huge, but yeah, the trend is. Okay. So the question is, can we find more evidence? I just want to present more data, and then I'll stop. Go ahead.
10% is a huge distribution shift.
I know, man. Well, it feels like it's a small distribution shift, and it's manifested in a huge error. So I guess the other way I'd say that is small distribution shifts seem to propagate into large. Like imagine what happens in reality, right? I mean, this is like one of these. Something I'd say. I mean, this is trying as hard as we possibly could to match the statistics. Maybe we could have tried harder, but it's a small distribution shift induces a large error, and we should be worried about that. I'm more worried about that than the diminishing returns we were seeing.
I mean, but what's also surprising that in both plots, you would imagine that the fragility increases as your models.
It doesn't, right? So clearly all we have to do is go from 600 million parameters to 600 billion parameters, and we'll be up on the line, and then it'll be fine, right? I guess. Then we'll have cheese self-driving, and full self-driving will happen once we get up there. But yeah, I don't know. I mean, I don't know how to extrapolate this any farther because we've all run. Even at Google, they've run out of resources. Yeah.
Is it clear that the way that Imagenet was built is actually even IID? It seemed like so.
No. And actually, I think the test set.
It's very close. When you do cross-validation with the validation set for Imagenet and fold it into the training set and so on, you get basically the same accuracies.
I mean, that's evidence. That's evidence.
Sure, it's not that's IID, but
let me show more plots. This is enough. Video. You want lunch? You don't want to see plots? Temi wants to see plots, man. You want to fight with Temi? I have a date bar in my bag. Okay. So, right. So this is a cool one. Same time. This is a curated data set from 2015 by the original Imagenet folks, right? Here there were 4,000 videos, but then they just rendered them down as 1 million JPEGs, and then presented to you as JPEGs. And each of these corresponds to some classes. It's a 30 classes, a subset of Imagenet. And so, but we know exactly where these images came, and it was supposed to be for video, but you could just use this for detection and classification. And what we did is we invented a metric, a fairly reasonable metric, which is you treat each video as a set of similar images, and then for every frame, you pick a K, and you look in the neighborhood of that K, and you see if you can find one where you get a misclassification. And this just allowed us to prune through that data set pretty quickly. Right? And so remember that these are all mostly 30 frame per second videos, so 10 frames is about a third of a second. Okay, so here's some cool pictures. You see these kind of pictures on Twitter all the time, where we go from a domestic cat, and within 10 frames, it's called a monkey. Let's see what a monkey is. Oh yeah, I think it's because I don't know. Anyway, now I see a monkey. This one I don't see. It goes from bird to domestic cat. I guess that's what it's eating. I don't know. This one goes from turtle to lizard. This one goes from dog to horse. What's amazing is these images to you look the same. I mean, I have to tell you to squint to see why they're different, right? And again, they're within a third of a second of each other. And of course, Jason can't see you. That's right. To Jason, Jason has a good filter that makes them all look the same. They all are cats. All are cats. We made a lot of effort to like make sure when you're going through here that the kinds of things we were pruning when we actually get to this next plot were like these. So the ones we saw before look really similar. These look really different. Right? These are very different. We pruned those. They did not go into the data set when we were doing curation. So we did this again. I didn't do this. Ludwig, Vaishal, also Dave. We recruited people from CMU for this. I mean, it's like a lot of work to label. And we see the exact same plot, man. It's weird. It's weird. We see the exact same plot. So that again, like just using this metric, you see again this big shift. This again, it's a small distribution shift. It's within 0.3 frames. This is 10. This is PM10. So it's within 0.3 seconds of each other. You see it's a small distribution shift, and again, everything. You don't see adaptive overfitting. You do see some sensitivity to distribution shift. Let me skip this because I'll talk about the end. Finally, Kaggle. Two more things. Kaggle released a nice meta-analysis or meta-data set of all of their competitions with a lot of information. Not all the information we would have liked, but a lot of information. Everybody knows on Kaggle you have a public and a private leaderboard. The nice thing is almost in every competition here, those are IID split from each other. So this is cool because now what we should see is that if you train the public leaderboard and you train and you somehow evaluate on the private, you should just see clustering around the y equals x. And that's exactly what we see. Clustering around y equals x. And it's not just on 2, it's on like these. How many did we do, Ludwig? I forgot the number now. 117. I don't have all of them in here. But you really see in this case, because you have IID splits, you just see clustering around the y equals x. So now, again, evidence that distribution shift, because these are IID. Evidence here is that this distribution shift is really what's causing us to be pushed off. Okay, I'll stop there. Oh, sorry. The most important slide, of course, is that because there's only one data set, right? The data set to make all data sets. We see Leon Batu wrote this beautiful oral history of the MNIST data set and also managed to reconstruct a bunch more examples. And it's a very nice, it's a real fun read. And again, we see the distribution shift again between these two test sets.
Is the slope still greater than one there?
Because he flipped them here.
This is error.
Yeah.
This is error, and we were doing accuracy, so it should be negative, right?
Yeah.
Yeah, I didn't want to. I just cut this out of their paper. I should have remade it. But anyway, cool. All right, so I'll stop there. In some sense, like we've seen this before. We know this. We knew this was true in boosting. That interpolating training data, we knew that was fine, and it did seem to always make your building bigger models seem to have better test error. Making your model big doesn't hurt. But there definitely does seem to be some other issues that are going to really be the pressing ones that we need to deal with moving forward. The big ones moving forward, I'm not sure, Jonathan and I will talk about how we teach this too in our undergrad machine learning class, just very gently, I think somehow. But I do think that for us, for researchers, and for anyone in industry, the bigger issues are this distribution shift is a real dangerous thing, right? If you're putting it in a car or you're making healthcare decisions, and like I could show you, if you're interested afterwards, I could show you a paper which demonstrates that actually a lot of there's huge distribution shift effects in all of the radiology, the deep learning for radiology, huge things where you're basically overfitting to the machine that took the image. So that's dangerous if that's a life and death situation. We already know that Tesla cars kill people. What's amazing about Tesla cars is 2 people have died driving under trucks with their autopilot on in Florida. And what's nice about that is that's machine learning generalization. You should never make the same error twice. I showed you your corner case, and yet 2 years apart, same error, same accident. So this is a real thing, and something we have to think about. But I think this is also cool. There were no theorems in this talk. Plenty of work to do in that space. Oh, there were 2, right? There were 2 theorems in this talk. We'll talk to Shai whether or not they actually passed the test later. All right, with that, everybody should go get lunch. Thank you.
Since we are late, so we're just for the lunch.